I'd just like to thank Barbara and Claude for inviting me to give this talk. I really enjoyed yesterday. We had lots of talks about the LAB, and I thought it was really refreshing to hear about so-called normal lithosphere and normal structure. And I guess today I'm going to start by talking about areas where we actually break up lithosphere, where we get continental rifting, and specifically talk about what seismic evidence we have for the controls and processes in this region. And I guess the subtitle for the work is really, 10 years of field work in Ethiopia. And I really would like to acknowledge all the people that have been involved in this work. It's been a really multidisciplinary, interdisciplinary adventure. Many different institutions have been involved in the work, but I'd really like to acknowledge a lot of the young scientists, PhD students and postdocs who have helped with the various facets of not only the seismology, but all the other components, the petrology, the geochemistry. And specifically, I'd like to acknowledge James Hammond, Ian Bastow, Manilo Balachu, and Derek Keir, who I think cumulatively have spent over 2 years doing fieldwork in Ethiopia. And it's really because of their hard work that we've really put together, I think, an exceptional seismic data set that is publicly available. So the East Africa Rift System, if you really want to study continental rifting, this is the place to go. It's often known as the Great Rift if you extend it up into the Red Sea. And it's exceptional in that it really covers the whole transition from really juvenile rifting down the south in Malawi. The rift system splits around the East African Plateau with the Kenya Rift and the Western Rift. It goes through the Turkana Depression and then get into the more advanced stages of continental rifting in the main Ethiopian rift, and then really we're at the stages of incipient oceanic rifting or spreading in the Afar Triangle or the Horn of Africa. And at this point we're at a triple junction between the Red Sea and the Gulf of Aden, which are obviously a bit more advanced. We already have a sea or an ocean opening up, but we really, if you look at the whole system, cover everything right from the juvenile stages to really the final stages of rifting. On the right here, the red dots are the seismicity and seismic events. The earthquakes delineate the rift structure quite well. But the green triangles, which are a bit fainter, are volcanoes. And what you can see is you move into the much more mature areas of rifting, there's a lot more volcanism, there's a lot more magma involved. And that's sort of a telltale sign of the shift in the controlling processes. And eventually, this is what Africa will look like. The Nubian plate and the Somalian plate will rift apart, and we'll get a new ocean in this area. So continental rifting is a really fundamental component of plate tectonics. It shapes the planet that we live on. And actually, rift valleys have really played a key role in the evolution of life on the planet. Once you start getting elevation, you get microclimates, you get rainfall, and it's easier to grow crops. And also, once you get elevation, it's easier for bipeds like humans to get away from much faster quadrupeds. So rifts have played a key part in the habitability of the planet. But having said that, plate tectonic paradigm's been around for a long time, and yet why continents rift apart and open and close in sort of Wilson cycles is still somewhat enigmatic. This result sort of summarizes work from a real seminal paper from Cindy Ebinger and Martin Casey, and it sort of shows how in the more juvenile stages of rifting, strain and deformation is accommodated by faulting, and you get these big border fault systems set up. And then as things advance, you start to get some axial magmatism and volcanism, and you get spectacular scenery like this. This is James Hammond sitting on the Ethiopian plateau looking down into the Rift Valley on one of these big border faults. And the change in elevation, it's a 2-kilometer drop off that cliff here. So it's pretty spectacular scenery. And then as things become even more advanced, the strain is really accommodated more in the magmatic segments and less in the border faults. And in Ethiopia, this gives rise to this, exciting volcanoes like the Erta Ale volcano, where there's a long sustained lava lake in the middle of the volcano. And just to give you an idea that rifting processes aren't really, sort of slow or over geologic time. We were, I guess, fortunate in 2005, a segment of the Bahu Rift segment in Afar opened up over a 2-week period. And this is where it was sort of most extreme. You can sort of see the signature of the rift. These are people on the edge for scale. So this is a really dramatic rifting event. And when you talk to funding agencies, this is a once in an academic lifetime event. And really the last time something like this happened above sea level was Krafla in Iceland in the 1970s. And what was exciting about this is it was the first rifting event of this type above sea level in the era of satellite geodesy. So things like GPS and INSAR have been really helpful. And very quickly, a team of UK, Ethiopian, and US scientists deployed seismometer and campaign GPS instruments around the region, and it led to a large multinational consortium. And this, here's Tim Wright's and colleagues' INSAR anomaly, and it shows the segment of the Dabahu Rift that opened. This is in a very remote part of Afar, so few people were affected. And initially we thought that it was magma injection associated with the deflation of these two volcanoes, Dabahu and Gabho. We now realize actually it was more magma injection somewhere in the middle of the segment, and actually a large depression has since occurred in the southern mark. And so after the initial diking episode, there's been at least 14 since then, some with additional eruptions also. So it's very, very exciting and giving some really unique insights into rifting and the generation of new crust in these environments. So here's a picture from a paper that's almost 10 years old now by Roger Buck, and it just sort of kind of shows a conventional idea of continental rifting. So in response to either some distant forces or forces beneath, you get a broad zone of stretching. The deformation's accommodated over a very, very large area, and mantle starts to upwell, and you'll essentially get some decompression melting and melt forming in this area. And given a normal geotherm, this sort of shows the yield stresses that are required to break the plate. And many hundreds of megapascals, especially in the lower part of the plate, are required to rupture things. So if you like, this is sort of the more conventional view of things. So why is Africa rifting? What forces are available? Well, there's distant forces, which are probably quite weak. Gravitational potential energy, which I'll say a few words about, but not too much. Ideas of basal traction associated with density-driven flow from the underlying mantle. And then there's obviously the contributing effect of pre-existing weaknesses and lithospheric thin spots. So Africa, was mentioned a few times yesterday. It's quite a unique continent. It's not moving particularly quickly in an absolute plate motion sense. And what's really remarkable about it is its dynamic topography. It's perched anomalously high. And this has really been attributed to the presence of a large low-velocity anomaly, or a superplume. This is a tomographic image of the shear velocity structure below Africa, running from sort of off southern Africa all the way across Afar and across Arabia. So at the core mantle boundary below southern Africa, there's a very low velocity anomaly which inclines upwards, and in the upper mantle comes out in the sort of main Ethiopian rift and towards Afar. And the anomalous dynamic topography of Africa is attributed to the density-driven flow associated with this upwelling. And here's a paper that describes the gravitational potential energy. Essentially, because the continent is high, it wants to get back to an equipotential, and so that provides a significant force that can be used for rifting. But even as the authors of this paper, Stamps and others from Purdue, say that there is not sufficient, even with this, there's not sufficient strength to overcome the forces to overcome the strength of continental lithosphere. So as Buck pointed out, there's a bit of a plate force paradox, and that the forces are an order of magnitude too small to break thick, cold continental lithosphere. So we'll come back to that as a theme. So just as Hitoshi showed us a cartoon from a textbook in Japan, this is one from the UK, and a famous image from Dan Mackenzie, sort of showing how, in response to distant forces, we stretch the mantle like toffee. It gets extended. we get these large faults, and then hot upwelling mantle will start to decompress, and we'll start to get melt generation across a very, very wide zone. And so as a seismologist, my question is, how can we better image this and better understand this? So we heard a lot yesterday about receiver functions. We can look at discontinuity structure, for example. We can look at how the thickness of the crust and the VP-VS ratios in the crust. We can use tomographic methods to image where we may have melt and where we have structure in the mantle associated with rifting. And then finally, we can use seismic anisotropy to look at flow patterns, the flow regime around rifts, and to look at if there's evidence of aligned melt or fabric or layering in these areas. And I'm going to show you results from these sort of 3 different approaches. So very often, to get rifting, a plume is invoked, or a plume certainly helps things along a bit. And for many decades, people have talked about the AFAR plume, and I guess another question for a seismologist is there seismic evidence for a conventional-looking plume in this area? And one way we might look for that is tomographically imaging it, but another is, again, using receiver functions to see if there are conversions off the 410 and the 660 kilometer discontinuity, and if there's a hot plume coming through this region, the mantle transition zone will be thinner because the 410 will be depressed and the 660 will be elevated. So we could look for evidence of that. And similarly, as Kate discussed yesterday, we can look for lithosphere, asthenosphere boundary topography also associated with plume impingement. So, as I said, there's been a lot of field work done over the past decade, and these are the 2 consortia, the 2 UK consortia that have helped acquire data. And really, there's been a campaign of French, American, UK, Ethiopian, and Eritrean scientists that have really blanketed this area. And it's quite remarkable. When we first started talking about doing work in Ethiopia, you couldn't really leave instruments out for more than a few weeks. And really, in the hot season, temperatures in this area are getting well above 50 degrees, and it's a very difficult area to work in. But now with modern instrumentation, you can leave things for at least a year. Over 200 instruments have been deployed in various campaigns through this whole area. And we've even had a number of instruments now in Eritrea, and more recently in Yemen, and we're hopeful to get a few stations in Somaliland in the near future. It covers an area that's roughly 800 kilometers by 800 kilometers, and elevations that range from well over 3,000 meters to well below sea level. And just some fieldwork pictures. It's a spectacular area to work in. This is a seismic station in Eritrea on the Nabro volcano, which exploded or erupted a few years ago. Here's a station near the Somalia border. It's challenging. The weather can change a lot, and as you can see from the camel, it's rewarding, but sometimes quite tiring. So I'll just quickly go through some of the results. And I won't talk much about the techniques. We've had some really good introductions to them yesterday. So as I said, there's this well-known large low shear velocity province, one of 2 on the globe that sits below Africa. And an interesting question is really what's the architecture of it as it interacts with the upper mantle, and really what happens as it again interacts with the lithosphere. And that's sort of where we now have resolution to say something about this. And the results are somewhat surprising. These have been published in a series of papers led by Ian Bastow and James Hammond. And we don't see a conventional plume-like upwelling. There's a broad, elongate corridor of low velocities in red here that run from the southern part of the main Ethiopian rift up into Afar, and it really fans out. And you can see the cold Pan-African lithosphere either side of it. So it's kind of like a knife edge that's come through the lithosphere. If we look in more detail, this is what the tomography looks at a depth of 75 kilometers. These are the P waves on the left and the S waves on the right. So warm colors are low seismic velocities. Blue, colder colors are higher seismic velocities. And in some ways, it's kind of the most expensive experiment to tell you where the rift is. And really, the low velocity zones delineate the main rift trend really nicely. And then you get these really, I think, somewhat startling right angle bends, especially here in the shear waves, as you move into Afar. And so, and you get punctuated upwellings or low velocity zones suggestive of rift segmentation. So the onset of perhaps rift transform type geometries. And then under the Ethiopian plateau, there's lots of low velocity channels that move under this area. The Ethiopian flood basalt erupted some 30 million years ago in this region. And this side of the plateau is much higher than this side. And I think a lot of that's because of the presence of this warm, low velocity material under this side. If you go down in depth, though, below these punctuated upwellings, you get this broad carpet of low velocities. This is looking along the rift trend, and this we're ascribing or attributing to the flow associated with the super plume. The anomalies are large. We get very big R values or very large VP-VS ratios, and it's really hard to not invoke melt as a mechanism. And it's worth pointing out that these are the largest absolute delay times anywhere in the world. So again, there's reasonably good evidence that there's melt at play all through this region. Then we can start to look more at the stratigraphy of the crust and lithosphere using receiver functions with the techniques that were described yesterday. So here is the crustal thickness from so-called HK stacks, which James published a few years ago. And there's really dramatic variations in crustal thickness. Underneath the plateaus, we get thicknesses well above 40 kilometers. Then as you move into the main Ethiopian rift, it's more like 25 to 30. And then as you move into Afar, less than 20. And in the northern parts of Afar, we get crustal thickness that's down to 15 kilometers. So really dramatic variations. Again, here, this is where the border faults are. So as you move, the Moho topography is a much more dramatic reflection of the surface topography. If we look at VP-VS ratios, again, under the plateaus, we get these more blue colors as sort of more normal 1.7 VP-VS ratios. And again, as you move into the rift, they start to rise near 2 in this area. And then, the highest value we get is 2.3, which again is really unprecedented. Anything above 2, really you have to invoke melt to explain it. You can't do that with just normal mineralogy. And again, very sharp variations at rift flanks. So as others, as Stefan and Kate described yesterday, we can use common conversion point migration methods with the receiver functions to better look at the topography. This is just one profile from the Ethiopian plateau across into Afar, and here's it just shows you the abruptness in the Moho thickness. It really is incredibly sharp. We go from these more normal VP-VS ratios to crust that's really laden with melt. And we now understand that actually most of the melt's in the lower crust and not so much in the upper crust. But I won't talk about that. Just to quickly review what Kate presented yesterday, looking at the S to P conversions. Really the take-home message again is that we've got a clear LAB, probably accentuated because of melt underplating or melt at the base of the LAB, that really disappears as you move into the rift. These more magenta discs show areas where we think we see the onset of melting. The other key take-home message in this area is that we go from the LAB to this a clear LAB to something we interpret as the onset of melting, but this is occurring at fairly normal depths for passive upwelling. So what it's implying is actually the mantle temperatures aren't significantly elevated, which is interesting in itself. And then finally, let's look at seismic anisotropy. So we heard a bit about that yesterday, and it's normally attributed to the preferred alignment of minerals, which is useful because it tells you something about mantle flow, but also a very effective way of generating anisotropy is the alignment either in layers or the alignment of inclusions, and low velocity or melt-filled inclusions are really effective ways of generating anisotropy. And so in an early paper we showed really what we expected to see was that the fast shear wave polarizations would be in the direction of spreading, as is seen at the East Pacific Rise, for example, in the MELT experiment. And instead, everything aligns with the rift direction. We get good alignment with the border faults, but more interestingly, the alignment rotates very convincingly to follow the magmatic segments, which suggests that a melt-induced mechanism might be at play. And so this was an early working model we developed, which basically said that, below the whole area, we've got sort of a multi-layer anisotropy. We have probably preferred crystal alignment associated with the density-driven flow towards Arabia. And then as the decompression melting starts to punctuate through the lithosphere, we get aligned melt inclusions that will be very effective at generating anisotropy. Off to the sides, we'll have a preserved fossil fabric associated with the Pan-African lithosphere. And then as you move into far, it's expected that we'd have preserved fabrics in continental slivers and microcontinents, for example, like the Danakil microcontinent. So to better address this, we've started using a shear wave splitting tomography technique. This is fairly new. Karen Fisher and her group also have developed a similar approach. We're using a methodology that was published by James Wookey a few years ago. And essentially, you can invert for domains of anisotropy, and how you parameterize that, really you guide by what you know of the tectonics and the geology of the area. It requires really good coverage. Ethiopia is sort of gifted in that we have really good seismicity from all directions, and we've had very long deployments. Some of these stations have been out for almost a decade, so there's really good data coverage. So we divide things into 2 layers and different domains across different tectonic regions of the area. And what's somewhat gratifying is that we find a really coherent lower layer. There's not a lot of variation in the lower layer. These little ticks give you the alignment of the fast anisotropy direction or the fast shear wave polarization. And they're all pretty uniformly aligned in this northeasterly direction. Below that is the velocity anomalies at a depth of 300 kilometers. You can see this big low velocity carpet. So again, we think this is a signature of the dynamic nature of this density driven flow below the lithosphere. But then as you go into the upper layer, things get a lot more complicated, as one might expect. This is actually some results from shallow shear wave splitting in shallow seismicity published by Derek Keir. And we get really large amounts of anisotropy near the axial magmatic segments. I mean, this is the Debahu segment, which opened in 2005, and it's really pronounced. Very short distance away, we get an orthogonal orientation, really small amounts of anisotropy. And this, we would argue, is the preserved anisotropy in the continental slivers that are being isolated. And these are the results from the topography. And we see lots of variations. In the main Ethiopian rift, it primarily aligns with the magmatic segments, but as you move into far, it becomes a lot more complicated, suggesting sort of a mosaic or a patchwork of slivers that are left behind. And so, as a result, what you're looking at is a really stratified upper mantle beneath the East African rift. We've got a broad, low-velocity region of density-driven flow, and then we've got these focused upwellings that are punctuating the lithosphere and crust, and we're getting this microplate isolation like the Danakil, which presumably is going to be eventually something like the Seychelles, where it's been drifting around in the new ocean. And if we go back to this Buck paper, what he pointed out in this paper, which was with great foresight, is that if you start to get dike injection into the lithosphere, you really dramatically weaken it, an order of magnitude weaker. And not only that, you really focus the deformation at the rifting point. And I think seismically what we've shown is really the fingerprint or the smoking gun of this process. We have this very isolated or very localized deformation. And in working with Ben Holtzman, we've pursued this a bit, looking at how melt would segregate at boundaries. And so, for example, you get melt segregation and strain partitioning, and this will help lubricate plate boundaries and, again, further facilitate rifting. So just in the final few minutes, I just want to show you what the transition zone looks like. This is work by Dave Thompson, and these are piercing points at 660 in red and 410 in blue. And these are just stacks. We see a very clear 410 and a very clear 660, a weaker 520, which is variable, which I'll show you in a minute. But really strong evidence for a low velocity zone on top of the 410 kilometer discontinuity. If you look in map view here, this is the mantle transition zone thickness. There's some anomalies towards the edge where we lose coverage, but where we have really good resolution, mantle transition zone structure is plus or minus 10 kilometers. It's really negligible, implying that this region is not anomalously hot nor cold. Okay, good. And then this is the tomography at a depth of 410, 520, and 660. So we see a broad, diffuse, low-velocity anomaly that's sort of poking through the transition zone in this area. But as I said, no really anomalous mantle transition zone thickness. Here's a cross-section running from north to south. And these are the very clear 410 and 660. And here's the 520, which seems to become a bit more apparent as we move to this low-velocity zone. And here's the evidence of this low-velocity region here. So one idea, one interpretation is that perhaps a plume has come through this area at some point. It's not there right now because it's not showing a thermal anomaly. It's brought water with it that's led to partial melting just above the 410. So going back to the sort of early cartoons, this is the old view of continental rifting, where we've got distributed deformation and stretching and the so-called afar plume. And this is sort of the emerging picture, which is nothing like that. We've got really abrupt flanks to the rift in the crust and lithospheric structure. We've got a broad low-velocity zone that underlays the lithosphere. There's no single plume coming up through this area, and we've got these punctuated upwellings that are coming through probably at pre-existing weaknesses. And then we've got a mantle transition zone that is not showing any obvious signature of a classic plume. So in conclusion, what we're looking at here are a broad thermochemical upwelling that originates at the core mantle boundary, these so-called large low-velocity shear provinces. And these give rise to perhaps more localized upwellings that come through the mantle transition zone. So in Ryan Gallagher's poster, there's an anomaly to the southern part of the main Ethiopian rift. Chan and Vanderlee showed similar anomaly under the Red Sea, and we're seeing something under southern Afar. But it seems to be smaller plumelets probably originating from the top of this thermochemical structure. We have a broad region of sublithospheric low velocities that underlie the region, and it's very dynamic, and the anisotropy is actually revealing this dynamic nature. And then we get punctuated upwelling, segmentation coming through that really mimic the surface structure. And I think the control really is top down in the upper 100, 150 kilometers, and that's why we have such a good mimicking of the surface structure. We have an eroded LAB beneath the rift, but the onset of melting, the depths we're looking at suggest that it's a more passive, what you see at a mid-ocean ridge, for example. And cumulatively, these observations really are the fingerprint of this magma-assisted rifting and do not support the more conventional simple stretching models. So everything's not resolved, obviously. There's I think some really key issues that we're struggling with. These are, as I said, these are the slowest travel time residuals on Earth, and yet seismically this region is not looking particularly hot, which is strange. And Kate discussed that yesterday in her results. But mantle xenoliths geochemistry actually suggests that it is hot. So we've got problems of reconciling two different data sets. This could be a question of resolution, I'm not sure. And again, we've got mantle transition zone topography that really looks unremarkable, very Prem-like. But there's maybe evidence of the fingerprint of water or partial melt above the 410. And it does sort of, I think, raise the question, is chemistry perhaps more important than thermal issues in this area? And are we looking at maybe the effect of exotic melts, carbonates and sulfides and other features? So I'll stop there and take questions. Thank you.